Good afternoon, class. I'm Dr. Temilola Oluseyi, and you're welcome to my class, virtual class 3 CHM 334. And just as we have been told when we started the course at the beginning of the semester, this course is divided into 4 parts of different spectroscopic techniques used for structural elucidation of organic compounds. And my aspects is on UV visible spectroscopy, and the second part of it is the mass spectrometry. I've already sent the materials for UV visible spectroscopy the last few days, and this is the second aspect of the course. My colleague, Dr. Olashuko, will be teaching you on infrared spectroscopy. I believe we've done that before the lockdown. And the second aspect will be nuclear magnetic resonance. So these 4 techniques are all we'll be looking at in CHM 334. But for today, we are having an introduction to mass spectrometry, a tool for an elucidation of structures of organic compounds. So when we talk about mass spectroscopy, we know that from the name, mass has to do with weight. And in mass spectrometry, the molecular weight of organic compounds can be obtained from very, very small samples. But this type of spectrometry technique has nothing to do with absorption or emission of light, like we were taught in the UV visible spectroscopy and the infrared spectroscopy. And that is why this is called spectrometry, not spectroscopy. But because of the word spec there has to do with the spectra, meaning that from the spectra or the spectrum, the molecular weight of organic compounds can be deduced. So what happens? How is this made possible in mass spectrometry? Here, a beam of high energy electrons breaks the molecule apart. So when the molecule, high energy electrons is focused on the molecule can be broken. We know that organic compounds are majorly brought together, or the type of bond you have there is a covalent bond. So these bonds can be broken when high energy electrons are focused on such molecules. So instead of using light, in this case of mass spectrometry, we make use of a beam of high energy electrons. And when the molecules are broken apart and the bonds are cleaved or broken when energy is applied, the masses of these fragments and their relative abundance will give us an information about the structure of the molecule. So it's like you have a puzzle and you break your puzzle into different pieces. You can arrange or bring the pieces together, and that will give you a picture of an idea of what the whole picture is all about. So mass spectrometry, some can be shortened as mass spec or MS. So in the course of the lecture and subsequent lectures, I may be using the word mass spec or MS. Is the same thing as mass spectrometry. And like I've said before, it makes use of high energy electrons to break a molecule into fragments. And when this is done, the fragment gives us information about the molecular weight of the compound. And not just the molecular weight, it gives us information about the structure. So we get the molecular weight or the molecular mass and the structural formula of the compound. So these are the 2 key information that the fragments that are broken from the molecule give us. These fragments or the molecule itself, sometimes in some textbooks, they are referred to as parent compound, or while the fragments are referred to as daughter ions. You'll see later on that these fragments are ions that are obtained when a molecule is broken down into fragments. So by definition, mass spectrometry is an analytical technique that measures the mass to charge ratio of charged particles. So mass spectrometry measures mass to charge ratio of charged particles, and it is useful for the determination of masses of particles, for determination of elemental composition of a sample or molecule, So apart from knowing the mass, it also tells us the composition. For example, I can say if the molar mass of a compound is 28, 28 can be carbon and oxygen, that is CO. And 28 can also be another compound may have the same mass as that 28. Nitrogen molecule N2 is 28. Carbon monoxide is 28. But it's not just enough for us. So many compounds may have the same mass, but the mass spectrometry goes further than just giving us the mass. It tells us the elemental composition of a molecule. So for example, if I have a molar mass of 28, mass spec is able to tell that this 28 actually belongs to 2 atoms of nitrogen. A molecule of nitrogen is 28, or it's an atom of carbon and oxygen in carbon monoxide that gives rise to this 28. So it gives us not just the mass, it gives us the elemental composition of the molecule. And when we know the elemental composition and we know the mass, we'll be able to know the chemical structure of the molecule. So oftentimes, mass spectrometry is, in this case, as this course is applied, is for organic compounds. Though later on, there are some mass spectrometry that is used for inorganic, but for this course, we'll be dwelling on the organic compounds that are elucidated using mass spectrometry. So as said previously, the mass spec principle consists of ionizing chemical compounds to generate charged molecules. So the chemical compound is ionized. A neutral chemical compound is firstly ionized, and after the ionization, a charged molecule is obtained. Then these molecules are now broken down into fragments, and these fragments are also ions. So the mass to charge ratios of these fragments are measured, and also the mass to charge ratio of the charged molecules are equally measured. So let's look at some terminologies that you're familiar with from your O-level chemistry. We know an atom is made up of protons, electrons, and neutrons. Your electrons are negatively charged, about 0.0005 Dalton. Your protons are positively charged, +1, while your neutrons are not charged. So the atomic number is simply the number of protons. So an element, the number of protons, they give the atomic number. You know, hydrogen has 1 proton, so the atomic number is 1. And that's just number of protons in an element. The mass number is the combination or the sum of the number of protons and the number of neutrons. So now, like the one we have on the slide, you have an hypothetical element K. K here is not potassium K, any element. And you have the Z, which is the mass number, and the sum of the protons and neutrons, while A is just the number of protons, and it's your atomic number. You know that the surrounded, you have your protons and electrons, and the protons and neutrons in your atom, and is now surrounded by electrons, or a cloud of electrons. Talking about atoms, we have another terminology that is commonly used when we talk about atoms is isotopy. And that means that it's possible for some atoms to have the same atomic number, but different atomic weights. And what brings about this is when they have different number of neutrons. Remember, your atomic mass or your molecular weight is the number of the atomic number and number of neutrons. So they may have the same atomic number, but different number of neutrons. And when this happens, such elements they are referred to as isotopes. Look at the example of hydrogen. Hydrogen has an atomic number of 1 because it has just 1 proton. But it's possible for hydrogen to have just 1 proton and no neutron. Hydrogen can have 1 proton and 1 neutron, or 1 proton and 2 neutrons. And that is why you have 3 isotopes: your hydrogen, your deuterium, and your tritium. You can see what is common to them is that it's the same atomic number, but their weights, their atomic weights differ due to the number of neutrons they have. Another example, common example, is chlorine. We have chlorine that has an atomic mass of 17. The atomic number is 17, meaning that chlorine has 17 protons. But alongside the proton, it also has neutrons. There are different number of neutrons. So you could have chlorine with 18 number of neutrons, and you have chlorine with 20 number of neutrons, and that gives rise to differences in the number of their atomic weight. So you have chlorine 35, and you have another isotope of chlorine 37. Another one is carbon. We have carbon, the most common carbon, which has 6 protons and 6 neutrons. Atomic number of carbon is 12, is 6, sorry. Atomic number is 6, so your carbon is expected to have 6 protons, but it has different number of neutrons. It has one isotope has 6 neutrons, another one has an isotope of 7 neutrons, another one has an isotope of 8 neutrons, and these three are the different forms of carbon. And in nature, these isotopes exist in different really abundance. One is more abundant than the other. We see that in the due course of the lecture. So the atomic mass, we have the absolute atomic mass unit, which is measured in Daltons or AMU, the atomic mass unit. So for chlorine, for example, chlorine 35, in nature, we have about 75% of chlorine in nature is chlorine 35, while about approximately 25% of chlorine in nature is the second isotope of chlorine 37. And so the mean atomic mass, you can calculate that by multiplying the relative abundance by the mass number, the atomic mass unit, and you add the two together and find an average of that. So 75% of 35 and 25% of 37 gives us the mean atomic mass of chlorine to be approximately 35.5. Another halogen that exhibits isotopy is bromine. Bromine has an atomic mass of 35, meaning that it has 35 protons, but number of neutrons differ, and we have bromine 79 and bromine 81. And finding this 50% of 79 plus about 50% of 81 will give us approximately 79.9, which is about roughly 80 Daltons or 80 atomic mass units. So you can see that, and in nature, the two isotopes of bromine are almost equal in abundance. While for chlorine, chlorine 37 is about a third of chlorine 35. So we know how to calculate the molecular mass. It's just the molecular mass. We have the molecular formula of the compound, and the formula will tell us the number of the atom present in the molecule. And the relative atomic masses can have with the addition of each of them. So you have the carbon 12 has a mass of the relative mass of 12.000 grams per mole, and this is the basis of where our other masses are obtained. On the periodic table, you always see that your relative atomic masses are integer values, like hydrogen is always 1, nitrogen is 14, oxygen is 16. But in the real actual facts, these are just the approximate integer masses. The real masses are based on their ratio to the carbon 12. And that is why the mass spectroscopy is able to determine the relative atomic masses up to the 5 or 6 decimal places. And so it's different. So if you have an atomic mass of 28, let's look at nitrogen, for example. Nitrogen will not give us 28 precisely with a mass spec. It's going to give us 28.00614. While your carbon monoxide, CO, which is also 28, is going to be 27.9949. So mass spectrometry has the capacity of determining to define it level of the atomic mass of the combining atoms present in a molecule. Another common terminology that we use in mass spectroscopy is M/Z. And this is a dimensionless quantity. And this is just simply mass of an ion divided by the charge. Remember that we talked about the molecule will be bombarded by an electron to become a charged molecule, and the molecule then breaks down or gets fragmented into ions. So what we are majorly measuring in mass spectroscopy is the charge to mass to charge ratio. and that is your M over Z, where M is the mass of the ion relative to carbon-12, and your Z is the charge. And oftentimes, your Z is always positive when we talk about positive ions, and it's always 1 unit. So most times, the M over Z is actually the mass of the ion, because Z is always or almost always positive, and it is 1 plus 1. So your M over Z will always be your mass. So when we talk about mass spectroscopy, what is the output of your mass spectroscopy is your mass spectrum. And the mass spectrum is a graph, and I'll show you the graph, and this is a graph of the mass spectrum. You have your y-axis and you have your x-axis. So on your y-axis, you have the relative abundance, and on the x-axis, you have the mass to charge. Remember the M over Z, we said mass to charge ratio. And because our Z is always almost 1, so this axis can also be taken as the mass. So we have the absolute abundance. That is the abundance of the detector. We look at the detector later on. So when an element gets, or a compound gets into the instrument, there's a detector that picks there's a response generated by the detector. That's the absolute abundance. Then we have what we call the relative abundance, which is the abundance that is normalized to the most abundant peak. So if this is the most abundant peak and is on a scale of 0 to 100, so the most abundant peak is the peak that has normalized to 100, and every other peak that you see in the spectrum they are normalized based on the one that is 100%, which is called the base peak. So the base peak is the most abundant peak, and it is always 100%. So if you look at this spectrum now, this peak at mass 83, if you trace it to the y-axis, is 100. So this is our base peak. So when you have an array of ions, the one that has the most abundant relative abundance is usually called the base peak. And we have the molecular ion. The molecular ion, like I've said before, is the parent ion, and it is the unfragmented charged molecule. So your molecule originally is not charged, but when a high beam of electron is focused on it, it becomes charged and becomes and it's intact. So it's the unfragmented charged molecule, which is the parent ion. And if you look at it, your molecular, this is a compound called the chloroform, CHCl3. If you look at CHCl3, carbon is 12, fluorine is 35, and you now have your hydrogen 1. So the molar mass of this is 118. So in this spectra now, the highest M over Z value there is the molecular ion. But you'll be wondering, you have 122. We'll get to that later. These are the isotopes. In case this molecular ion is based on the normal mass of chlorine to be 35. But peradventure, one of these chlorine atom is chlorine 37. The mass will not be the same thing as this 118. The mass will be different. So other things we see there is the M over Z, which is the mass to charge ratio. And we have what we call the radical cation. The radical cation is a positively charged ion with odd number of electrons. A radical cation is a positively charged ion with odd number of electrons. So, and looking at this now, if this is our molecular ion, we see some other lines or spectra, lines in the spectrum, and these are called the fragment ions. Remember I said that the molecular ion or the molecule is charged and is bombarded with an electron and is broken into pieces. The covalent bonds are broken, and these are the fragment ions that are broken off from the molecular ion. And you can see that they appear at different integer masses, which corresponds to the mass to the charge ratio. So you have a peak at 87, 86, 85, 83, and it goes on and on like that. And these are all the possible fragments that are generated from this molecule. And one thing that strikes, you can say there's a fragment at 35. Means that maybe if one chlorine atom fragments, you see a charge, you see a mass at 35, you see another mass at 37, which may likely be the isotope of the chlorine 35. We'll see that later when we start talking about fragmentation patterns. So now let's go to the introduction of this technique. So this mass spectrometry is a powerful analytical technique which is used to quantify known materials, to identify unknown compounds within a sample. So we use it for both quantitative and qualitative analysis of organic compounds. And like mentioned before, it is used to elucidate the structure and chemical properties of compounds. So the complete process involves the conversion of a sample into gaseous ions. So the sample or your molecule is first converted into gaseous ion with or without fragmentation. Then later on, fragmentation occurs, and the fragment ions and the molecular ions are characterized by their mass to charge ratios and their relative abundances. So this technique of mass spectroscopy studies the effects of ionizing energy on molecules. And it also depends on the chemical reactions in the gas phase where the molecules are consumed while in the formation of the ionic and neutral species. When we get to the instrumentation, you understand this better. So the main information that is given in summary in the mass spectrometry is the molecular weight of a compound, the number of specific elements based on isotopic peaks. It gives us the molecular formula with high resolution, and also the fragment patterns are reproducible. So different functional groups have their fingerprint fragmentation pattern. The way an alcohol will fragment will be different from the way a carboxylic acid compound will fragment. And that gives us the identity. So there are some things to look for in your fragments that will give you an idea that, oh, this compound is an alcohol. Even between alcohols, the way a primary alcohol will fragment will be different from the way a tertiary alcohol will fragment. So the identity of your compound from the fragments gives us what functional groups we're dealing with. Just like your infrared, you have your absorption bands for different functional groups. And you can say when you run your infrared, you can say whether it's a ketone or an aldehyde or a carboxylic acid. The same way, the fragment patterns are also fingerprints that is useful in mass spectroscopy to know the kind of functional group or the arrangement of atoms in a particular molecule. So it's not just enough for us to know the molecular weight or the molecular formula. We also need to know the arrangement of the compounds or the molecule that generates such spectrum. So what is the basic principle of the mass spectrometry? And this, what measures this is called a mass spectrometer. So what measures the spectrum that we've seen before is an instrument called a mass spectrometer. So what the mass spectrometer does is generates multiples of ions from an organic sample that is being investigated. And these ions, those multiple of ions are the fragment ions that are obtained from the parent of the molecule. So when these ions are generated, they are later on separated according to their specific mass to charge ratio. And if you go back to the slide we had here, these ions, you can see them that they are separated according to their masses. The mass to charge ratio, they are separated. There's 35 from 37 to 48 to, and the likes up to the highest M over Z value. So they are separated according to their mass to charge ratio, and they are recorded. So the relative abundance of each ion is now recorded. So the first step in mass spectrometric analysis of compounds is the production of the gas phase ion. So your compound is first vaporized by electron ionization. So when your compound, whether it is liquid or solid, that's introduced into the mass spectrometer, there will be a production of ions in the gas phase. Then this molecular ion that has been vaporized now undergoes fragmentation. And each product ion or fragment ion derived from the molecular ion can also further fragment and be broken down into other fragments. And that is why some text would refer to these fragment ions as daughter ions. I know it's only women that can give birth. They are not called son ions. They are called daughter ions because they can also further fragment and give birth to other daughter ions as well. So you have your parent molecule. It gets ionized in the vapor phase and later on gets broken down into fragments. And the fragments also can be broken further down into other fragments, and that's called fragmentation of the molecule. The principle also involves the ions are now separated in the mass spectrometer according to their mass to charge ratio, and they are detected based upon their relative abundance. So invariably, a mass spectrum of the molecule is produced, and the results are displayed as a plot of abundance, ion abundance. If you remember, the ion abundance was on the y-axis, while on the x-axis, you have the mass to charge ratio. So the ions that are obtained gives us information about the nature and the structure of the molecule that gives rise to them. And like I always explain, is that you have all this jigsaw puzzle. The puzzle might be the picture, maybe the map of Nigeria, and it's now broken into different 30. There you now have pieces of 36 Ole plus 1, 37 Abuja. You now have the map of Osun, Ogun, Ondo, Kebbi, Katsina, Akwa Ibom, all the states as different pieces, and you are now told to bring all this together to form a whole map of Nigeria. So until you bring all the pieces together, you can never have a complete representation of the map of Nigeria. So exactly the same way, when you have the fragment ions, all the fragment ions must be brought together, and that will give us the information about the molecule that gave rise to those fragments. This is another example. So you have your abundance on your y-axis, and you have the charges, your M over Z value. And see here, this is 2,4-dimethylpentane. If you find the molar mass of this, the molecular ion, the molar mass is 100. And this is the entire molecule here, while all these are the fragment ions that were produced from this parent molecule. And you could look at that there is a fragment that has the highest relative abundance and the scale of 100, and this is called the base peak. And every other ion abundance is relative to this peak that has the peak at 41. And one thing you need to know, that the base peak is the peak that is the most stable of the ion that is usually assigned as the base peak. So some of these are the words that will always come across while in the course of this lecture. The molecular ion, the ion that is obtained by the loss of one electron from the molecule, and is usually put as a radical cation. Then you have the base peak, which is the most intense peak in the mass spec, assigned 100% intensity. You have what we call the radical cation. They are positively charged species with odd number of electrons. We'll see that later. Then we have the fragment ions, which are the lighter cations, and they are the fragments obtained from the molecular ion. They are formed by the decomposition of the fragmentation of the molecular ion. And this often corresponds to stable carbocations. We'll see that later. And we have what we call the mass to charge ratio, M over Z. And I said the M is the mass, while the Z is the charge, which is usually +1. So your mass to charge ratio is always the mass of the molecule. Like for example, here we have 2,4-dimethylpentane. The M over Z is 100, and that corresponds to the molar mass of that compound. So this is the schematic diagram of the mass spectrometer. Remember, we said that you have, this is the probe where the sample is introduced. You have the ion source, and the ion source has a beam of electrons that when the sample is introduced, this beam of electron will ionize this molecule, and this molecule now becomes vaporized, and it passes through the slits, and you have some electromagnetic regions where the ions are now deflected according to their mass to charge ratio. And at the end of it, you have a detector that detects the ions as they arrive at this point. So different ions, remember that when the fragmentation occurs there, you have different M over Z values of these ions. And the very light ones will travel faster than the heavy ones because the fragments are in different masses. If you look at here, we have fragments of, you have a mass of 100, 85, 57, 43, 41, and they will not travel at the same speed because they have different masses. So each of these ions will arrive at the detector at their different masses of that. So this is the mass spectrometer, as I said before. So the ions are now accelerated towards the detector. And if you look at it, the ions that are too heavy, this electromagnetic segment of it, the ions that are too heavy will bend a little. Ions that are too light will bend very much because it's a curved magnet, but they will arrive at different points. And one thing is to also know that the mass spectrometer is always kept under vacuum because of we want to, it must be pressurized. So as each ion arrives at the detector, there is a recorder that picks the signal of each ion as they arrive. And this is connected to a PC or a computer, and you have a visual display unit where your ions are, your spectra is seen. So you'll be able to draw this instrument. So this is just, it's the same thing. So the samples are ejected. There's a heater that heats it because that's been vaporized. There's an electron source, and you generate ionized sample, and the samples are accelerated. These are magnets, and these are the different magnetic region. They are deflected round about the curve, and they arrive at the detector. You can see the lightest one, the heaviest one will arrive much later. So the magnetic field is generated, and it separates these particles that are obtained from here according to their mass to charge ratio. So what are the main components of the instrument? You have the ion source, we call the ionization source, or the ion source, which will convert the molecule into the gas phase. Then we have the mass filter that separates the ions. We have the detector that detects the ions. So the separation of ions is through the electromagnetic region. Then the ions are detected. So the most of them run in this order from 1 to 2 to 3. But you can have these two can be broken further into different steps. You can have 1, 2, you have ionization, you have the fragmentation of the separation, and these ions can further be ionized again and be separated, and finally you detect them. So you can have them in steps 1, 2, 3, or 1, 2, go back to 1 again, ionize again. And what happens is that when your ions are generated there, they can go back again and be ionized again and begin to be fragmented until it gets to the detector. So is the mass spectrometry or mass spectroscopy is a very common chromatographic detector. It can be coupled to a liquid chromatography or gas chromatography. So we've said before, so the three major components, as we've said before, is the ion source, and we need to know what happens at each of these components. So the ion source is where the gaseous ions of the substance are being produced. The analyzer is where the ions are resolved into their different components based on their mass to charge ratio. And you have the detector system where the ions are detected and the relative abundance of each of the resolved ionic species are recorded. Then we have the sample introduction system. That is where the samples are introduced into the ion source. And remember that you have to maintain a very high vacuum in the instruments, and you have the computer always added. And this is just where you control the instruments, where you set the temperature, the pressure, and the likes. The computer also is used to acquire and manipulate the data to store the data and to compare spectra from different libraries. So this is also the instrumentation again, the sample introduction from the inlet. You have the ion source or ionization source where the ions are vaporized into the gas phase. You have the electromagnetic analyzer where the ions are sorted or separated according to their mass to charge ratio. You have the ion detector. As they arrive, they all arrive at different times, just like you're running on a field or a track, and everybody, according to their speed, will press the tape at different arrival times. So this detector detects them each time an ion reaches there based on their mass to charge ratio. And you have the software where this data system that integrates the data, and you have your spectrum, which is the output that can be displayed on the screen of your computer and as well stored in the PC that you can retrieve it later on. So the function of the mass spectrometer said it produces ions from the sample at the ionization source. The samples are separated according to their mass to charge ratio with the mass analyzer. Then each fragment that have been broken are now analyzed in the analyzer. Then the detector detects them and the signals are processed by the computer. So samples can be introduced as solids or liquids on a probe, and that's called the direct insertion probe. And this probe will be heated. Remember that the sample will be vaporized in the ionization chamber. So it will be heated. And mass spectroscopy is suitable for pure substances. It's not for mixtures. It must be pure substance for you to be useful. And that is why when it's coupled to a gas chromatograph, the GC will separate the ions. And when the ions are separated, they are separated in the ions are separated based they are according to their mass to charge ratio, but they must be pure substances. And also the volatile liquids and gases can also be sampled, but there's a way you introduce them into the ion source, right? Instead of people, because they're already volatile and they're in gaseous phase. So they don't need to go through insertion via the probe. They are directly introduced into the ion source because they're already vaporized, and that will just flow into the ion source and the journey starts from there. And so samples can be introduced into the mass spec after the separation using the gas